For the last couple of class meetings, we have been discussing the concept of magnetically coupled circuits, right? And part of that was an understanding that we observed magnetic coupling whenever we had two coils that were physically close to each other, such that the flux being generated by coil one induced a voltage in the second coil, and similarly, any flux being produced by coil two passed through coil one, inducing a voltage there. So wanted to make sure that there was some form of magnetic coupling happening. In that case, we might wind our coils on the same piece of core material. Okay. So I might have something like this, where I have a cylinder made of some particular core material. And I could wrap one coil around it like so. Let's say, for the sake of argument, that I1 is flowing in this direction, and our voltage V1 has this polarity. And over here on the bottom part of the cylinder, I might have another coil. Let's say that our voltage V2 will have this polarity when our current I2 has this particular direction. So in this system, thank you, any flux that's generated by coil one will definitely wrap around and flow through coil two, like so. So we have a system in which we are ensured that those two coils are magnetically coupled. Now, the amount of flux that's generated through from coil one passing through coil two isn't going to be necessarily all of it. We can see very clearly that there's some flux leaking out the top and leaking out of the bottom, right? So another way that we could make a similar system like this would be to use a core that itself forms some closed loop. There are multiple ways that we can do this, but one of the most standard ways would be a rectangular core, something like this. So if we had a rectangular core like this, we could wrap a wire around one leg of this core to form a coil. Just for the sake of argument, we'll have I1 in this direction and B1 with this polarity. And this particular coil has N1 turns. And then on the opposite leg, or some other leg of this rectangular core structure, we could also wrap a wire. Like so. Call this I2 B2 of T, and this second coil has N2 turns. In this configuration, with a well-chosen core material, meaning one that is particularly ferromagnetic, what we would see is that all of the magnetic flux generated by coil 1 winds up passing through coil 2, and we have formed what we're going to talk about at the beginning of ELET 360. We formed what's called a magnetic circuit. Okay, we're not going to talk particularly much about magnetic circuits today. We are simply going to recognize that these structures are what are commonly referred to as a transformer. So when we have two coils that are forced to be magnetically coupled to each other because they are both wrapped around the same physical structure, we have formed a transformer. If we were trying to make a quick and dirty transformer, it would probably be like something on the left. Most actual professionally made transformers are more similar to the structure on the right, where it's wrapped around a closed magnetic core. The reason being is to keep all of the magnetic flux internal to the structure so that we get the most efficiency out of the system as is possible. Okay. So for transformers, we have magnetically coupled coils, so there is obviously some amount of mutual inductance between those two coils. It's often expressed in terms of a coupling coefficient K. Okay. So for a transformer, let me write this better. Coefficient lowercase k defines the degree of coupling between the two coils. So generally speaking, if our coupling coefficient is between 0 and 1/2, we would consider that we have loosely coupled coils. If K is between 1/2 and 1, we have tightly coupled coils. And if K is exactly equal to 1, we have perfectly coupled coils. And I'm going to write over here, whenever our coils are perfectly coupled, we have what's called an ideal transformer, which we're going to talk about at length on Thursday's class meeting. But today we're going to talk about the more general case. Okay. So the value of K depends on the physical geometry of the system as well as the material that the core is made of. And we are going to explore these relationships in much greater detail when we talk about magnetic circuits in our next class together. For now, we are going to define our coupling coefficient K in terms of the self and mutual inductances of the coils in the system. So mathematically, K is equal to the mutual inductance divided by the square root of the products of the self-inductance. And from this relationship, we can see that in order to achieve perfect coupling, our mutual inductance M has to be equal to the square root of L1 times L2. All right. So we've talked about the coupling coefficient here. For the purposes of this class, we can really think of it as just an alternative way to describe the mutual induction term. So for example, if I gave you a circuit, something like this, or I had, let's call this 10 angle 0 degrees volts. This isn't particularly going to matter. 8 ohms of resistance. Let's have a coil here with an impedance of J5 ohms. Let's have a coil here with an impedance of J10 ohms. A 20 ohm resistor here. And I could say that these coils are mutually coupled together and K is equal to 0.3. This is just a way for me to say, well, now you have to do a couple of steps to figure out what M is and then treat this circuit exactly like we would have done previous, right? So in this case, M would be the square root of, or I guess the impedance M, a better way to put this, would be the square root of 5 times 10. So the square root of 50, or 5, excuse me, square root of 2. And so as an impedance, this would look like J5 root 2 ohms of mutual inductance between those two coils, right? So K is equal to 0.3 is just a different way of expressing that value of M, and vice versa for the intents and purposes of this class. All right, so now we are going to talk about some tips and tricks that we can use in order to solve these magnetically coupled circuits, or now these transformer circuits, if we didn't necessarily have a computer available to us. So for simplistic circuits, we can define something that's called the input impedance of our transformer. Okay. So let me write something down here. In addition to two coupled coils, a realistic transformer model also includes some resistances, R1 and R2, which account for ohmic losses in the coils. So effectively, all of this statement means is that because our transformers are usually made of real wire, and real wire has a resistance, we should account for the resistance of that wire as part of our transformer model. So instead of simply having our coils, where this would be L1, and just for the sake of argument, I'm going to put a dot here. And then on this side, I'll have my coil L2. Put a dot here. So this would be a simple transformer model. We are now going to include some resistance R1 in series with coil L1, representing the actual physical resistance of that coil. And we are going to have some resistance R2 here, representing the physical resistance of coil 2. I'm going to label these terminals for my transformer model here, A, B, C, and D. And what we will often see is that terminals B and D are tied together, representing some common neutral point for our circuit. Okay. So kind of running out of space here. We're going to get into some nomenclature things here really quickly. We would refer to this side of our transformer system, the left-hand side, typically because we read things from left to right, as the primary windings of our transformer. And the right-hand side will be the secondary windings. Yes, ma'am. Yes, ma'am. So realistically, we are not using the impedances at all. We are using the actual value of the inductance measured in henries and the actual value of the mutual inductance measured in henries. So I kind of skirted around something here. So let me do a little bit better job of explaining it, right? So if L1 and L2 are measured in henries, what we actually have access to here is J times omega times L1 and J times omega times L2, right? And up here, we would expect to be able to represent the, the impedance of our mutual inductance as J times omega times M. So I have posited here that omega times M, I'm just going to throw away the J just for the sake of argument, because it's just going to mess things up a little bit here, mainly because I'm taking a square root, is going to be omega times L1 omega times L2, which would be the same as omega times the root of L1 times L2, and the omegas wind up canceling each other out on either side of the equal sign. So we're going to get the same exact results if we just use the reactance part of the impedance, meaning we throw away the J. We would get the exact same results doing that as if we had access to the nominal value of the inductances measured in henries. So I was playing fast and loose. Yeah, it's gonna exactly right. Yeah. All right, so we have our primary and secondary defined here. So let's say that we applied a voltage source over here to the primary windings. Let's call this VS. And we loaded our secondary windings with some arbitrary impedance Z sub L. Okay. So from the standpoint of the voltage source, everything to the right of terminals A and B can be represented by a single equivalent impedance, despite the fact that there is, oh, and I should label the mutual inductance here. Despite the fact that there is magnetic coupling going on, we can treat it as one single impedance. So I want to talk about how we could do this. So if we write a KVL equation at the primary side of our transformer, what we would have is negative VS plus, let me label my currents here, doing a poor job. So let's say this is my current I1, and this will be my current I2, and I've chosen this particular direction for I2 just so that it's flowing into the dotted terminal of coil number 2 here, just to be clear. So I would have a total impedance of R1 plus J omega L1 being multiplied by I1, and then I will also have a J omega M times I2 and set this equal to 0. So before I go any further, are we okay with the sign on the mutual inductance term? This could easily be rearranged to show that VS is simply R plus J omega L1 times I1 plus J omega M times I2, right? Just moving the VS term to the right-hand side, excuse me, to the left-hand side of the equal sign. Anyway. Now we could write a KVL equation around our secondary. So I'm going to write our mutual inductance term first, and we'll see why here in just a moment. We're going to have J omega M times I1 plus R2 plus J omega L2 plus ZL times I2 is equal to 0. Right, so I have my mutual inductance term because of my magnetic coupling, and then I2 sees all three of those impedances as if they were in series. And I can rearrange this expression and find that I2 is just negative J omega M I1 divided by R2 plus J omega L2 plus ZL. Everybody okay with my algebra here? Nothing too wild or crazy. Right. If I substitute this relationship into this relationship, what I will have is VS is equal to R plus J omega L1 times I1 plus j omega m times I2. And I'm going to substitute in what I just found I2 to be, negative j omega m divided by R2 plus j omega L2 plus ZL, all of that times I1. So that I would have R plus j omega L1 I1. So what happens when I multiply j and negative j? Positive 1, absolutely right. So plus omega squared m squared over R2 plus j omega L2 plus ZL, also multiplied by I1. And now I can define my input impedance, Z in. So this is the impedance I would see looking into terminals A and B of my transformer as the ratio of VS over I1, which comes out to be R plus j omega L1 plus omega squared m squared divided by R2 plus j omega L2 plus ZL. So we have two terms here. The first term is simply the primary loop impedance. And it is exactly what our voltage source would see if we didn't have any mutual inductance in the system whatsoever. And then our second term is what we call our reflected secondary loop impedance. So we call it a reflected impedance because it's the impedance on the secondary as seen by the primary. So it's not going to look like the same thing. It's actually scaled by this factor of omega m squared to show us what it looks like on the primary side. And we could also reflect things from the primary to the secondary, looking in at the other set of terminals if we wanted to. And that's something that we're going to do an awful lot in our later classes and trying to figure out how to most simply analyze lots of different electric machinery circuits because they all effectively wind up having an equivalent circuit that looks extraordinarily similar to that of a simple electrical transformer like we're talking about now. So I'm just trying to lay some groundwork for what we're going to be doing in our later classes. So for the purposes of this class though, let's see how this concept of input impedance could be utilized to aid our circuit analysis, right? So let's say that I have the following circuit. I have a 120 angle 30-degree volt source over here on the left. Three ohm resistor, a minus J2 ohm capacitor, and then a coil having J5 ohms of impedance here. Let's put our dotted terminal on the top for this particular section of the circuit. And then on my secondary side, I have a J20 ohm resistor, which is the inductor. There is J2 ohms of mutual inductance between these two coils. Here I have a minus J4 ohm capacitor, 6 ohm resistor, and a 4 ohm resistor. And I'm trying to find the value of this current I1 and the value of this current I2 for this particular system, right? So this is something that we absolutely know how to do because we've done it in our last couple of class meetings by effectively setting up a system of equations and using a computer to solve that system for these currents I1 and I2. But I would argue that we can actually use this concept of input impedance, which I've just introduced, as a way to solve for these two currents without having to use a computer. Okay? So we can literally just use our exact equation, or at least a version of it that we just developed. Okay, so my input impedance consists of two terms, right? My primary loop impedance and my reflected secondary loop impedance, where that's just the secondary loop impedance and omega squared over m squared divided by the impedance of the secondary loop. So what should the impedance of our primary loop look like here? So what's the real part going to be? There's only one resistor, so let's start there. 3, okay? So I feel very strongly that it's going to look like 3. And then I have minus J2 in series with plus J5. So what's that? Plus J3. So we're going to get to that. That's part of the reflected secondary impedance, right? The omega squared m squared part in the numerator up there is the only place that that's going to show up in, right? So just to be clear here, when we were deriving all of this stuff, this R1 that we have right here is really taking the role of this 3 ohm resistor in series with this minus J2 ohm capacitor. Similarly, R2 is just taking the role of the 6 ohm resistor in series with that minus J4 ohm capacitor, right? So our end result, we saw R1 plus J omega L1, which is our primary loop impedance here, plus omega squared over m squared divided by the impedance of our secondary loop, which was just R2 plus J omega L2 plus that load impedance ZL. So what is our secondary loop impedance? So I have 2 resistors and they're in series. So what do? Add them together. So what's 6 plus 4? 10. And then I have a J4 ohm or a negative J4 ohm impedance capacitor in series with a J20 ohm inductance coil. So what are those two things added together? J16. What's omega m? So it's everything but the J. So it's just going to be 2 ohms. Right. So throw this in your calculator. What do you get? When I did it, I got 3.112 plus J 2.820 as a rectangular form complex number. And I got it as 4.2 angle 42.181 degrees ohms as a polar form number. So take a moment to do this, make sure you're getting the same thing that I'm getting. Okay. So we found the input impedance for this simple transformer circuit. So how can we use this to solve for our currents? Right? Well, we know that Zn must be equal to Vs over I1. So we could rearrange that and say that I1 is then simply Vs over Zn. So that's going to be 120 angle 30 degrees volts divided by that 4.2 angle 42.181 degrees ohms, which I get to be 28.571 angle negative 12.181 degrees amps. How am I going to solve for I2? So if we were to write a KVL equation just around that left-hand side, like we've been doing in our previous things, we would have, I'm trying to do it to where we can see it at the same time. Excuse me, 120 angle 30 degrees volts would be equal to 3 plus A3 ohms times I1 plus, what was our mutual inductance here? J2 ohms times I2. We know everything in that equation except for I2, so we can solve for it. All right. So I2 would be simply 120 angle 30 degrees volts minus 3 plus J3 ohms times I1, which we just found out was 28.571 with an angle of negative 12.181 degrees amps. All of that divided by J2 ohms, which I got to be 3.029 with an angle of negative 160.176 degrees amps. No computer necessary. So let's take a look. You guys have a question? Where's my penmanship crappy? Yes, 0.176. I will write that better. 176. Is that more clear? No. Any other things need prettying up? Got to get a new tip for my stylus soon. I've worn down the point to a flat nub thing that's not drawing as prettily as I would care for. All right, So pretty straightforward for a simple circuit like this. Let's take a look at something a little bit more complicated. So let's say, just for the sake of argument, that I was trying to find the equivalent impedance of this network. Yes. I will rewrite that, hopefully make it look better, like a 10. And just to be clear, that's 20. Any others unclear? Okay. And then I have mutual inductance here of J4 ohms, right? So I want to figure out what my input impedance here would be. Now, we don't have a clearly defined primary and secondary here, so this one's going to be a little bit more tricky, right? So what we can do is something very similar to what I did to derive the relationship when we had a clearly defined primary and secondary side. We could write a KVL equation around our first loop, write a KVL equation around our second loop, and then do a little bit of algebra, right? So if I wanted to find the equivalent impedance here, I could apply some test source. Let's call it 1 angle 0 degrees volt for the sake of argument. I'm going to define this current to be I1 and this current to be I2. Writing my KVL equations, I would have 1 angle 0 degrees volts is going to be equal to, so let's see, I'm going to simplify things here. So when I'm following I1 around its path, it's going to see that 4 ohm resistance, and it's also going to see that 10 ohm resistance. 4 plus 10 looks like 14. It sees negative J2, positive J6, so that's going to look like J4. And then it also is going to see the mutual inductance term. So let me think about this really quickly. No. All right, so the 4 and the 10 together is 14. Then I have J6 and minus J2, so that's going to look like plus J4 ohms times I1. Then I'm going to have my mutual inductance term, which is just going to be plus J4 ohms times I2. Is everybody okay with my Kirchhoff's voltage law equation here? Anything not making sense? Because the current I2 is flowing into the dotted terminal of the second coil. So my I1 is flowing into the dotted terminal of coil 1, which is the J6 ohm inductor, and I2 is flowing into the dotted terminal of the J8 ohm inductor, so my mutual inductance term should be positive. If the current I2 were in the opposite direction, or the current I1 were in the opposite direction, both of them being in the opposite direction would keep it positive. But if either of those currents were in the opposite direction, the mutual term would be negative. Thank you for that. You're absolutely right. So I missed that. So what Bailey had just mentioned. So I'm definitely going to have a plus J4 ohms for my mutual inductance term multiplied by I2. But the 10 ohm resistor there also sees a current of I2 and it's flowing into the negative terminal. So that would look like negative 10 plus J4 I2 to me. Thank you very much for that. Or this exercise would have come out very poorly when I show you the easier way to do it here in a moment. So it relies on me doing it the hard way correctly in order to show you the easy way and have the answers come out the same way. So I very much appreciate that. All right, any other errors or simple mistakes that I've made here? I believe I've accounted for everything. So there is exactly a current of I1 flowing through the 4 ohm resistor. And then there's a contribution of I1 flowing through the 10 ohm resistor. So that's why I added those two guys together. Negative J2 plus J6 is positive J4. My mutual inductance term is represented by the plus J4 I2, and then I'm also taking into account that I2 is flowing in the opposite direction as it flows through the 10 ohm resistor, which is why it looks like minus 10 down there. So once again, I'm lumping a couple of steps together because we've done this enough times. Maybe I shouldn't have, maybe I should have done it more formally, but we'll get through it. So now let's look at our KVL equation around our second loop. Right. So in our second loop here, we're going to have negative 10 plus J4 times I1. Because as we follow I2 around, I1 is in the opposite direction. So that's where the minus sign comes from for that 10. And then our mutual inductance term is still going to be J4 times I1 in this case. And it's positive because both of our currents are flowing into the dotted terminals. And then I2 sees a total resistance of 30 plus J8. Let me write that ohm sign better. This will be equal to 0. Anybody have any questions, comments, or concerns about my second KVL equation? Did I manage to do this one right on the first try? I think so. Okay. So rearranging this second equation, we could see that I2 is just going to be negative 10 plus J4 ohms over 30 plus J8 ohms times I1. So I'm simply moving this term to the opposite side of the equal sign and then dividing both sides by that 30 plus J8. I'm going to throw this in my calculator here really quickly so that we can just express it simply as a number. So negative 10 plus 4i over 30 plus 8i looks like 0.347 with an angle of negative 36.733 degrees, unitless, times I1, and I'm going to store that in my calculator as X. Or actually, to be clear here, I'm storing this thing in my calculator as X. If I substitute this relationship in, I have 1 angle 0 degrees volts will be equal to 14 plus J4 ohms times I1 plus negative 10 plus J4 ohms times what I have is X, 0.347 angle negative 36.733 degrees times I1, and therefore Zn is just going to be 1 angle 0, my test voltage, divided by I1 is 14 plus J4 ohms plus negative 10 plus J4 ohms times that 0.347 angle negative 36.733 degrees. Which I get to be 14.030 with an angle of 30.813 degrees. Ohms, and then I could use this in order to find the currents and all kinds of things like that. Okay. So this method, not wildly difficult, but definitely tedious and prone to mistakes. I say that because I certainly made one. And again, thank you so much, Bailey, for pointing it out, or this would have gone even more poorly than it's going. So let's talk about how we could approach this from a different perspective. Okay. So what I'm going to do now is I'm going to introduce what's called the T equivalent model for a transformer. Okay. There's also a pi equivalent model, which I'll introduce, but we're not going to really use it. Okay. So transformer equivalent circuits. So what I am positing is that if I have a transformer like so, containing a coil that has some inductance L1 and a second coil that has some inductance L2, and I am the dots are on the same side here. I'm going to call this A, B, C, and D. I can replace this with following network. Where here are my terminals A, B, C, and D. Okay. So in order for me to do this, I have to make sure that these two networks are electrically equivalent, which means they have to have the same voltage drop across their terminals. So if I have a voltage V1 here, I have to have the exact same voltage V1 here. If I have a voltage V2 here, I have to have literally the exact same voltage V2 here. And my currents have to be the same as well. So I'm going to define a current I1 flowing in like this, which means I would have a current I1 on this side. And I'm going to define a current I2 like so that I would have to have a current I2 like this. So what I'm going to do is I'm going to write KVL equations for both of these systems. Okay. So on the left-hand side here, I could say that V1 is equal to J omega times L1 times I1. And V2 is equal to, excuse me, plus, forgot the mutual, which is the point of this, my bad. J omega M times I2. And I write my KVL equation for the secondary side effectively as transformer, and I'm going to get V2 is equal to J omega M times I1 plus J omega L2 times I2. If I write my KVL equations for this equivalent network, or what I'm trying to make equivalent, I would have J omega LX plus LZ plus J omega LZ times I2. I forgot my I1 there. My apologies. What happens when I'm deriving it from memory? And V2 would be J omega Ly plus LZ times I2 plus J omega LZ times I1. I'm going to rearrange these guys really quickly so that I have the I1 term first and the I2 term second, just so that it'll be very easy to see what I'm trying to give you. J omega M I1 plus J omega Ly plus LZ times I2. Okay. So what we're going to do is just use these relationships very simply to figure out what LX, LY, and LZ are in terms of L1, L2, and M. So let's start with something easy. What do we think LZ should be by looking at these equations? So I have this term right here, J omega LZ times I2 by itself. Oh, well, I made a mistake here because this should be LZ. Right. And then I have this term right here that also has LZ by itself, J omega LZ times I1. And that corresponds to this part of this equation and this part of this equation. So I ask you again, what do you think LZ should be in terms of L1, L2, and M? Just M. Absolutely right. So LZ is just M. Okay. So what about L1? So we have this term right here. which corresponds to this term right here. So I believe that L1 is just Lx plus Lz, or Lx plus m. From this, we could say that Lx is just L1 minus m. And very similarly, we have this term right here and this term right here, which must be equal to each other, which means L2 has to be equal to Ly plus Lz. We know that Lz is equal to m. So therefore, Ly is equal to L2 minus m. So these are the relationships if the dots are on the same side. What do you think is going to happen if the dots are on opposite sides? Change the sign on M. That's it. So, with that in mind, let's revisit this thing and see if we can find the equivalent circuit or the equivalent impedance more quickly, right? So, I had $4 ohms in series with minus J2 ohms. Here I have J6 dot on top, J8 dot on bottom, J4, which looks terrible. Let me write that better. I'm just going to make a couple of labels here. So this point right here is A, B, C, and D. So I can replace that with that T equivalent circuit model, which is going to give me 4 ohm resistor here, minus J2 ohm capacitor here. I'm going to put this as Lx for right now, Lz for right now, Ly for right now, this is what my equivalent circuit would look like. I've just replaced this network with its T equivalent right here. And now I need to figure out what the values of Lx, Ly, and Lz are. Well, my dots are on opposite sides. So Lx should be L1 plus M. So that's going to be J6 plus J4. Looks like J10 ohms. Ly should be L2 plus M. So that's J8 plus J4. J12 ohms. And then Lz should be negative M because the dots are on opposite terminals. So that's just going to look like minus J4 ohms. And so to me, my input impedance for this system looks like 4 plus J8. So that's where I have minus J2 plus J10 in series, plus the parallel combination of Let's see, 10 minus J4 and 20 plus J12. Let me write that 12 better. 10 plus 20 is 30. 12 minus 4 is 8. So take a moment and throw this in your calculator and tell me what you get. Try that again. That isn't what I got. So let me type it in again. I did too, which is kind of the point. So 4 plus 8i plus 10 minus 4i times 20 plus 12i over 30 plus 8i. I got 14.030 with an angle of 30.813 degrees ohms, which is literally the exact same thing we got here, doing it a much longer way, right? Yeah. So this T equivalent circuit can absolutely be used to simplify things. Now, there's also what's called a pi equivalent circuit, right? So let me write this up here. This is what we call our T model. Our pi model, we draw it like so. So if this is L1 dot on top, this is L2 dot on top. Terminals A, B, C, and D. And just to be clear, I need to define my voltages V1 and 2, my currents I1 and 2. We could also express this as a pi equivalent circuit. It's called a pi equivalent circuit because arguably this is going to look somewhat like the Greek letter capital Pi. Here are terminals A, B, C, and D. Here's our voltage V1, our voltage V2. I'm going to call this guy over here LA, this guy right here LB, this guy right here LC. Here's my current I1. Here's my current I2. And LA is simply equal to L1 times L2 minus M squared over L1 minus M. LB is L1 L2 minus M squared over L2 minus M. And finally, LC is equal to L1 L2 minus M squared divided by just M. I'm not deriving this because this is just the delta transformation of that Y model that we just had. So effectively, the delta Y transformation that we developed at this point a month and a half ago for three-phase circuits could absolutely be used to transform this thing as well, giving us these results. And using that transformation is way easier than deriving it like we did the other one. So these are the results. All right, so these are two different equivalent circuits that we could use. My personal preference is definitely the T model because it's a little bit easier to use and it's the one that we're going to wind up using the most, but the pi model might be appropriate in some particular situations. Okay, so the last thing that I want to talk about for today is energy storage in a transformer. And to facilitate this, we are going to use the T equivalent circuit. So if I have a simple transformer where I have some coil L1 just realized I forgot to indicate the M on there. So L1 and L2, and they are magnetically coupled to each other. I could replace this network with our T equivalent circuit, where this is LX, LZ, and LY. The current flowing in here is going to be I1. The current flowing in here is I2. So what should my current flowing down through LZ be? Should it be the sum or the difference of I1 and I2? Sum. Okay. So the energy stored in my transformer as a function of time, let me actually come out on the left-hand side here, is going to be 1/2 LX times I1 squared plus 1/2 LY times I2 squared plus 1/2 LZ times I1 plus I2 squared. All I'm doing here is just using the generic equation for the energy stored by an inductor, because I can now treat this transformer as if it were 3 inductors, and the total energy stored is just going to be the sum of the energy stored in each individual inductance. Okay. Energy stored by an inductor is 1/2 Li squared. So substituting in our relationship for Lx, this is going to look like 1/2 L1 minus M times I1 squared plus 1/2 L2 minus M times I2 squared plus 1/2 M times I1 plus I2 squared. Breaking things down a little bit, we're going to have 1/2 L1 times I1 squared minus 1/2 M times I1 squared plus 1/2 L2 I2 squared minus 1/2 M I2 squared. And then let's FOIL this thing out here. So we're going to have 1/2 M I1 squared, 1/2 M I2 squared, and then 1/2 M I1 I2 plus 1/2 M I1 I2 looks like 1 M I1 I2. This bit cancels this bit. I forgot to write the 1 there, so my apologies. This bit, oops, cancels this bit. And we're left simply with 1/2 L1 I1 squared plus 1/2 L2 I2 squared plus M I1 I2. What do you think would happen if the dots were on the opposite sides? Change the sign on M.